This is Precalculus, section 2.6, rational functions and their graphs. So we'll go over the examples in this section and some of the information you need to know to understand better. So rational function, first of all, what is a rational function? A rational function is any function that is in a ratio form, fractional form, like this, p of x divided by q of x, where both p of x and q of x themselves are polynomials, right? Powers of x that are positive integer powers. So the domain of f of x is all x because polynomials themselves, their domain is all x, except you can't divide by 0. So q of x cannot be 0 here. So in our first example, we have g of x equals 5x squared divided by 8x squared minus 2x minus 3. And we want to find the domain. So all we say is it's all x except where this denominator is equal to 0. So let's figure out where the denominator is equal to 0 first. So we set 8x squared minus 2x minus 3 equal to 0. I notice in that process that this actually can be factored. If you didn't see that, you could use the quadratic formula, but this can be factored into 2x plus 1 times 4x minus 3, which means that if I set each of these equal to 0, x would be minus a half here, and x would be 3/4 here. So those are the two places where the denominator is 0, which means the domain of that rational function is all values of x except those two values of x. So to put that into interval notation, it would be minus infinity to minus 1/2, open parentheses, because we cannot include minus 1/2, union, which is or, minus 1/2, open parentheses, because we cannot include minus 1/2, to 3/4, open parentheses here, union, open parentheses, 3/4 to infinity. Of course, it's always open parentheses at infinity. All right, asymptotes. Vertical asymptotes are a line, x equals a. So all of these pictures show vertical asymptotes at x equals a. And what they are is it's where f of x either increases without bound, in both of these examples, or decreases without bound as x approaches a. As x gets closer and closer to a, think about that from either side, okay? Now, arrow notation, we use this. This notation here says as x approaches a with a superscript plus means as x approaches a from the right side of a, f of x approaches infinity. So as x on the x-axis gets closer and closer to a from the right side of a, the function itself, the y value, shoots off towards positive infinity. As x approaches a from the left, this minus sign means from the left. That's a superscript. This is not minus a. It means as x approaches a from the left. So as x approaches the value of a from the left side of a, f of x approaches infinity, right? F of x approaches infinity. In calculus, you'll see this as limit notation. You'll see this as the limit as x approaches a from the right of f of x, that equals infinity. The limit as x approaches a from the left of f of x equals infinity in this picture. And then likewise, you can see how that notation works on as f for both of these examples where f is shooting down towards minus infinity. So how do I locate vertical asymptotes of a rational function? Remember, we're talking about rational function. Essentially, you'd look for the zeros of the denominator again, unless the numerator is also 0 there. So if the numerator is also 0 there, that would be a removable discontinuity. It would not be an asymptote. Okay? So it's only an asymptote if the denominator goes to 0, but the numerator does not go to 0 there. All right, horizontal asymptotes. These are lines, y equals b. So horizontal asymptote, the function itself is approaching that line as either x approaches infinity or minus infinity, okay? So as x approaches infinity or minus infinity. These are all examples as that x approaches infinity, the function is approaching this line y equals b. As x approaches infinity, as x gets really, really big, the function is approaching the line y equals b. As x approaches infinity, the x gets really, really big. The function, again, is approaching y equals b. We don't care at all about what's happening over here, right? Over here, over here. We just care what's happening as x gets really big. You could also have asymptotes as x approaches minus infinity. So how do we locate those horizontal asymptotes? We locate those horizontal asymptotes by looking at the degree of the numerator versus the degree of the denominator, okay? If the degree of the numerator is less than the degree of the denominator, then y equals 0 is a horizontal asymptote. If the degrees of the numerator and the denominator are the same, then the horizontal asymptote is the coefficient, the leading coefficient in the numerator divided by the leading coefficient in the denominator. In other words, the coefficient of the highest power of x, which is the same as the highest power of x in the denominator. They're both the same in numerator and denominator, so you take their leading coefficients. That's the horizontal asymptote. And then if n is bigger than m, in other words, the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. Okay, our second example in this section is a company is planning to manufacture ATVs, all-terrain vehicles. The fixed monthly cost will be $200,000 and it will cost $2,500 to produce each ATV. So let's write the cost function first of all, C, of producing X ATVs. So the cost function of producing X ATVs, C of X, is whatever the fixed cost is. That's like, how much it costs to own the property, to rent the warehouse, to do whatever, plus the variable cost. The variable cost is what changes all the time. So the fixed monthly cost is $200. The variable cost is $2,500 for each X ATV. So it's 2,500 times X. So this is the cost function for manufacturing ATVs there. Now the average cost function is just like if you take an average, you add everything up, divide by the total number. So the average cost function of producing X ATVs is the cost function itself, fixed cost plus C of X, divided by the number of ATVs, X. So in this case, the average cost function is 200,000 plus 2,500X divided by X. So in part C, we are asked to find the average cost of producing 1,000 ATVs. So that'd be 200,000 plus 2,500 times 1,000, all divided by 1,000, or about $2,700 to produce the 1,000 ATVs. Now, if I were looking for what's the horizontal asymptote, then in other words, I'm looking for the horizontal asymptote of this function, the average cost function. So I notice that the degree of the numerator, which is a polynomial, is 1, right? Highest power of x I see is 1. The degree of the denominator is 1. So since the degree of the numerator and denominator are the same, the coefficients of those highest powers, 2,500 and 1, 2,500 divided by 1, would be the horizontal asymptote. That's essentially saying that as x approaches infinity, as the number of ATVs I make approaches infinity, the average cost to produce each ATV is 2,500. And that sort of makes sense if you think about it, because it costs that much to produce an ATV, 2,500, and by the time I start making so many ATVs, this fixed cost means very little. It doesn't mean anything. So it's an asymptote. We're approaching actually the variable cost here. All right, example 3. Find the horizontal asymptote of h of x equals 12x squared plus x minus 5 over 3x squared plus 4. So first of all, in a problem like this, you would need to recognize that you do have a rational function, a polynomial, divided by a polynomial. You check the degree of the numerator and the degree of the denominator. You see they're both the same. The degree of the numerator is 2. The degree of the denominator is also 2. So then you take their leading coefficients and divide them that way. So 12 divided by 3 is 4. That is your horizontal asymptote. As x gets big, either positive or negative infinity in this case, then the horizontal asymptote is 4. All right, so how do we graph rational functions? And this is still a skill that's important, not necessarily to be really precise with the graphing of them, because we have calculators and computers, etc., but there's a lot of things about the algebra and the understanding of rational functions that'll be important when you get to calculus. So being able to draw a quick graph, or at least understanding how these functions behave, will help you in understanding things in calculus. Okay, so this is a strategy. Please read through it, okay? I'm not going to sit here and read it through you, but you want to determine symmetry, which means you want to know if you have an even or an odd function, right? An even function would have y-axis symmetry, an odd function would have origin symmetry. Find the y-intercept by evaluating f of 0, right? When x is 0, that gives you the y-intercept. Find the x-intercepts by setting the function equal to 0, which really means just set the numerator equal to 0. Find vertical asymptotes, we know right now by setting the denominator equal to 0, making sure that it's also not where the numerator is equal to 0. Find the horizontal asymptote just by looking at the leading coefficients of the degrees if the degrees are the same. Plot at least one point beyond and between each x-intercept and vertical asymptote, and then use all that info to kind of get the graph nicely sketched. So in this example, I gave you a function that doesn't necessarily look like a rational function because these are not polynomials, but when you simplify this by combining this into one fraction divided by this combined into one fraction, you get a rational function. Okay, so this is a polynomial of second degree, this is a polynomial of second degree, and then we can go through and do all the steps here. Step 1 was look for symmetry, which means I want to look at f of minus x. If I plug in f of minus x and simplify, I don't get either f of x or minus f of x back. So there is no symmetry here, no y-axis and no origin symmetry. To find the y-intercept where x is equal to 0, I just plug in x is equal to 0. Notice that when I plug in x is equal to 0, I get minus 1 squared is 1 over 0. That's undefined. So there is no y-intercept. P of x, I look at the numerator, I set it equal to 0 to see if there's any x-intercepts. Set that equal to 0, I see that x equals 1, so here's my x equals 1, and I would plot that at this point, just plot that point. Set the denominator equal to 0 to see if I have any vertical asymptotes. So my vertical asymptotes, when I set the denominator equal to 0, I see that x can be 0 or minus 1. So x equals 0 is the y-axis, that's a vertical asymptote, and x equals minus 1 is a vertical asymptote. So I'm going to draw those in dotted lines. Of course, the y-axis, x equals 0, is already there, so you can't draw in a dotted line there. All right, step 5 was to look for horizontal asymptotes. All right, the degree of this numerator is 2, because if I multiply this out, I get x squared minus 2x plus 1. Its leading coefficient then is 1. The degree of the denominator is also 2, because if I multiply this out, I get x squared plus x. So the coefficient of x squared is 1 here, so 1 over 1. Y equals 1 is a horizontal asymptote. So I'm going to draw that in with a dotted line. These are not part of the curve, but these are asymptotes, so I like to draw them in with dotted lines. And then I'm going to plot points on either side of the asymptotes, etc. So these are just the values I chose to plot. You can look through those and see the evaluations. I plotted those, and then you take all of that information and sort of sketch in the curve, right? You know, that's an asymptote here, so that's going to shoot up towards this. This is an asymptote, it's going to shoot up. This guy shoots up to that asymptote. This guy would shoot down to y equals 1 asymptote. So you get a basic idea of what the function looks like.